look at your hand in the dim light of your room. Just really look at it. The iron flowing through the veins beneath your skin, the calcium that's, forming the very bones of your fingers.
Right, the carbon acting as the fundamental scaffolding for, well, every single cell in your body.
Exactly. None of it was made here. Every heavy atom inside you was forged in the catastrophic, luminous collapse of ancient, dying stars. I mean, billions of years before the Earth even existed.
It's true. You are, quite literally, made of exploded stardust.
And if you're joining us right now, it is highly likely that you are settling into the quietest hours of the night. You're ready to let that stardust rest.
Today is done.
Yeah. The demands on your time, your energy, your attention, they've all faded away. So we are going to do something a little different with our deep dive into the research today.
Different kind of pace.
Right. We're calling it an orbit into sleep. We are not going to rush. We aren't going to throw rapid fire information at you. Instead, we're just going to take a very slow, very gentle, highly detailed journey together.
Just let your mind unspool. Let it drift.
You can close your eyes, just listen to the sound of our voices. It's like a bedtime story for the wandering mind, really meant to ground you in the vastness of space.
Because tonight, we're going to trace the billion-year unhurried journey of cosmic dust.
The ancient, incredibly quiet, softly drifting material from which the entire cosmos is built. We'll follow it from the cooling breath of those ancient stars all the way down to the invisible rain of material that is falling on your roof tonight.
And there is absolutely no need to hurry. I mean, the universe as we know it operates on a timescale of roughly 13.8 billion years.
That is a lot of time.
Right. It has taken all of that time, all of those countless unhurried eons, to slowly assemble the world you are resting in right now. The cosmos is never in a rush.
And neither are we. And neither are you. There's no test at the end of this.
No, nothing you need to remember. If you fall asleep halfway through a sentence, that is exactly what we hope for.
We are just going to explore the meticulous, quiet machinery of the cosmos together at a pace that honors the deep time of the universe. So let's start by simply looking up.
Just picturing the night sky.
Yeah, imagine you are standing outside on a perfectly clear, deeply dark night, perhaps far out in the country, away from any city lights. You look up at the Milky Way.
That great glowing river of pale light stretching across the sky.
For centuries, when stargazers and early astronomers looked up at that exact same sky, they noticed these massive, unnerving dark patches.
Great inky voids in the glowing band where the stars just seem to stop completely.
Right, and for the longest time, the prevailing assumption was that these were simply holes. Empty gaps in the architecture of the heavens where absolutely nothing existed. It was, well, the ultimate illusion of emptiness.
And it's a profoundly natural assumption to make, especially when you're relying only on human eyes or early primitive optics.
Because if you look at a glowing wall of light and see a dark spot, human intuition just tells you there's a hole in the wall.
Exactly. You assume you are looking through a gap into the infinite empty dark beyond. But the history of the shadow, the incredibly slow generational realization that space is not empty at all, is one of the most beautiful awakenings in the history of astronomy.
It started very quietly, right? With meticulous observation.
It did. Back in 1847, a German-Russian astronomer named Friedrich Struve was engaged in this painstaking work of counting stars.
Night after night in the freezing cold of the observatory, just plotting their positions and their brightness.
And he noticed a statistical anomaly. The further away he looked into the galaxy, the fewer stars he could see per cubic light year.
But it wasn't because the universe was suddenly running out of stars at that specific distance.
No, it was because some invisible pervasive veil was steadily absorbing their light before it could even reach his telescope. He could measure the dimming mathematically, but he lacked the physical evidence to name what was casting the shadow.
If I try to picture what Struve was experiencing, it really makes me think of a thick, heavy winter fog rolling into a city at night.
That's a great way to visualize it.
Like if you look out your window and you can't see the skyscraper a few blocks away, you don't assume the building has been demolished or just vanished into thin air.
Right, you know the concrete and glass are still there.
It has just been veiled. The light from its windows is being caught, absorbed, and scattered by millions of tiny water droplets suspended in the chilly air. So the stars hadn't vanished. They were just hiding behind a cosmic fog.
But how do you prove the fog is there if you can't actually see the droplets?
That's the challenge.
You have to look for the things that remain still while everything else is moving. And that proof came decades later, in 1904, through the work of Johannes Hartmann.
He wasn't just counting stars, though.
No, he was analyzing their light through spectroscopy. Specifically, he was watching a binary star system. Two massive stars engaged in a slow, intense gravitational waltz, orbiting a shared center of mass.
And as they moved towards Earth and then away from Earth in their orbit, the light they emitted should have stretched and compressed right.
Yes, the Doppler effect. When a star moves towards you, its light waves compress and shift toward the blue end of the spectrum.
And when it moves away, the waves stretch and shift toward the red.
Exactly. But Hartmann noticed something impossible in his spectral readings. Amidst all this cosmic motion, certain absorption lines, specifically those of calcium, were completely stationary.
They didn't shift blue.
And they didn't shift red.
Which means those specific calcium atoms could not possibly be attached to the dancing stars. I mean, if they were, they would be moving with them.
You've got it. The only way those calcium lines could remain perfectly still was if there was an enormous detached cloud of cold calcium gas sitting perfectly stationary in the dark, empty space between our telescopes and those dancing stars.
So the starlight was passing through the cloud, and the cloud was leaving its still, quiet fingerprint on the light.
It was the first tangible proof of the interstellar medium. But the true, elegant proof, the moment we really discovered the solid dust grains themselves, not just the gas, came in 1930.
From Robert Trumpler, a very patient, careful astronomer.
Yes, Trumpler. His work is fascinating because he wasn't relying on massive explosions or anomalous binary stars. He was just looking at open star clusters,
which are essentially gentle families of stars drifting together through the galaxy, born from the same original cloud. And he was trying to figure out exactly how far away they were.
He was working at the Lick Observatory in California, peering through the Great Refractor Telescope. He studied about 100 of these open star clusters. And Trumpler measured their distance using two entirely separate methods, just to ensure his math was correct.
Always good practice.
First, he measured them by their apparent size. Simple geometry dictates that if two clusters are roughly the same actual physical size, the one that looks smaller in the night sky must simply be further away.
It is exactly the same way you judge the distance of a car on a long, straight highway at night.
Perfect analogy. Second, he measured their distance by their brightness. We know the intrinsic luminosity of certain types of stars, so if they appear faint, we can calculate precisely how much distance the light had to cross to degrade to that level.
Now, if I'm Trumpler and I have these two distinct mathematical methods to measure distance, I am fully expecting them to yield the exact same result.
You would hope so.
Right. If the geometry says the cluster is 1,000 light years away, the brightness should absolutely confirm it is 1,000 light years away. But if they don't match, wouldn't your first instinct be that your telescope lens is just dirty? Or, I don't know, the Earth's atmosphere is acting up?
Oh, absolutely. That is the mark of a rigorous scientist. You always rule out local interference first. But Trumpler was meticulous. He accounted for atmospheric distortion. He accounted for the instrumentation.
And yet the discrepancy remained.
And it was deeply consistent. The more distant clusters were unarguably fainter than their geometric size suggested they should be. It wasn't a random error, it was a compounding effect.
The further the light had to travel, the more of it was lost.
The only logical, inescapable conclusion was that the vast spaces between the stars were not a perfect vacuum. Space was filled with a fine, granular dust that was physically dimming the starlight. He termed this phenomenon interstellar extinction.
Interstellar extinction.
But in his data, he also noticed something deeply poetic about how the light was changing. The dust wasn't acting like a perfectly opaque gray wall, just dimming the light equally. It was changing the actual color of the starlight.
I assume this is a process of filtering, like looking at a bright light through a piece of colored glass.
It is a process called reddening, and it relies on the physical size of the dust grains themselves. These grains in space are incredibly tiny microscopic specks. When the broad spectrum of white starlight hits this cosmic dust, the light behaves according to its wavelength.
Right, because blue light has a very short, tight wavelength.
Exactly. And because it is short, it is highly likely to crash into these tiny dust grains and get scattered away into the dark, bouncing off in different directions. But red light has a much longer, lazier, rolling wavelength.
So it can just bypass the dust.
It is large enough to undulate right over and around the tiny dust grains. So the red light pushes right through the cosmic fog and reaches our eyes. When you look at distant stars through this interstellar dust, all their blue light has been stripped away,
leaving them looking warmer and redder.
It is the exact same physics that gives us a deeply red sunset here on Earth.
Because when the sun is low on the horizon, its light has to travel through a much thicker slice of the Earth's atmosphere, right? And all the dust and smog scatters the blue light, leaving only that blazing, lazy red to reach our eyes.
That is a beautiful connection.
But it completely reframes how we view the night sky. Those dark patches, the coal sack, the Great Rift, the famous silhouette of the Horsehead Nebula, they are the exact opposite of empty holes.
They are the densest concentrations of cosmic dust in our galactic neighborhood. There is a profound philosophical shift in that realization.
Because for generations, astronomers thought the dust was just an annoying nuisance, a dirty window blocking their pristine view of the universe beyond.
But it turned out the obstacle blocking the view actually was the view. What looked to the naked eye like an absolute terrifying void was actually a dense, rich, fertile nursery, brimming with the very raw material that the universe uses to build worlds.
Just let that image settle for a moment as you rest. The dark spaces are not empty. They are full. They are heavy with potential. They are waiting.
They are.
But this raises the most fundamental question. If the space between the stars is filled with this gentle, drifting, microscopic fog, where does it all come from? How does a universe consisting mostly of hydrogen and helium gas actually manufacture solid dust?
To answer that, we have to transition away from the quiet spaces between the stars and look at the stars themselves. Specifically, we have to look at how stars slowly, gracefully come to the end of their lives.
We need to look at what astronomers call asymptotic giant branch stars, or AGB stars for short.
Right. Think of a star very much like our own sun. For roughly 10 billion years, it lives a stable, highly balanced, deeply comforting life.
It exists in a state of hydrostatic equilibrium,
where the crushing inward pull of its own immense gravity is perfectly balanced by the outward pressure of the nuclear fusion happening in its core. It just quietly, patiently fuses hydrogen into helium.
But eventually, in the deepest depths of time, that core hydrogen fuel begins to run critically low.
And when that happens, the star does not simply switch off like a light bulb. It undergoes a magnificent transformation. The core contracts and heats up, while the outer layers do the exact opposite.
I picture this middle-aged star settling into its later years, beginning to swell. It expands outward, growing into a massive, bloated red giant.
If our sun were to enter this phase right now, its outer edges would stretch all the way past the orbit of Mercury, past Venus, and it would swallow the Earth completely.
It becomes enormous and diaphanous, and as those outer layers stretch further and further away from the burning core, they cool down. The star becomes unstable, it begins to breathe, it begins to pulse.
That pulsing is a deeply rhythmic, slow-motion expansion and contraction deep within the star's structure, driven by the varying opacity of the helium and hydrogen shells. And with every massive outward pulse, the star exhales.
Just breathing out into the dark.
It pushes its outermost layers of gas completely away from its gravitational grip, sending them drifting into the cold vacuum of space. This is what we call the stellar wind.
It's a slow, steady, continuous exhale, moving at just a few kilometers per second.
And as this shell of expelled gas drifts further and further away from the dying heat of the stellar core, its temperature plummets. And in that extreme cooling, something miraculous happens. The scattered atoms floating in the gas finally slow down enough to find each other.
When you say they find each other, we aren't talking about a random clumping. We are talking about highly specific chemistry happening in a vacuum. It is like molecular puzzle pieces snapping together in the deep freeze.
That is a perfect way to conceptualize it. It is a precise thermodynamic lock-and-key mechanism. At thousands of degrees, atoms are moving too fast with too much kinetic energy to bond.
They just bounce off each other.
Exactly. But as the temperature drops below specific condensation points, the chemistry activates. If the dying star is rich in oxygen, those oxygen atoms find silicon atoms. They align in the exact geometric configuration required to snap together into a stable crystal lattice.
They form microscopic crystals of silicates, minerals like olivine and pyroxene.
These are the exact same silicate minerals that make up the smooth, dark rocks you might pick up on a volcanic beach in Hawaii or Iceland.
So the universe is quietly manufacturing planetary bedrock, grain by microscopic grain, in the freezing breath of a dying star.
Now, if the star happens to have a higher ratio of carbon than oxygen, the chemistry shifts entirely. The oxygen is locked up in carbon monoxide gas, leaving the remaining carbon atoms free to find silicon atoms.
And what do they make?
They bond to form silicon carbide. That is a material so incredibly hard and resilient that we synthesize it here on Earth for industrial cutting tools and bulletproof vests. The universe has been forging it in the sky for billions of years, just letting it drift into the dark.
I find it endlessly fascinating that the universe is just up there, engaged in this slow, meticulous industrial manufacturing of beach rocks and diamond hard minerals.
It really is doing the quiet work of creation.
But let me pause and push back on the timeline of this process for a second. You mentioned that these AGB stars, these swelling, pulsing red giants, take billions of years to evolve into this dust-making phase.
Right, they are middle-aged stars.
But what about the very early universe, shortly after the Big Bang, before any star had the chance to live for 10 billion years and slowly age? How did the very first dust form in the dark when the universe was still young?
That is a crucial distinction to make. The early universe simply could not wait billions of years for a star like our sun to slowly age and exhale. It needed a much faster, far more dramatic forge to seed the cosmos with heavy elements.
You needed supernovae.
The magnificent, unimaginably violent collapse of massive stars. When a star that is 8, 10, or 20 times larger than our sun burns through its fuel, it does not swell gently. It runs out of outward pressure instantly.
Just a total structural failure.
In a fraction of a second, gravity wins. The entire mass of the star collapses inward at a significant fraction of the speed of light, hits the ultra-dense iron core, and then rebounds in an explosion of incomprehensible power.
But the true gift of that cataclysmic explosion is what happens immediately in its wake. A gift born from absolute destruction. The shockwave must be unfathomably hot, but space is deeply cold.
Yes. In the violently expanding shell of that supernova remnant, The gas expands so rapidly that it cools incredibly fast. And in that sudden, sharp drop in temperature, dust condenses out of the gas in staggering oceanic amounts.
We've actually seen this happen, right?
We witnessed this directly in 1987 when a star exploded in the neighboring galaxy, the Large Magellanic Cloud. It was designated supernova 1987A. When astronomers used infrared telescopes to look at the cooling remnants of that single explosion years later, they found a vast reservoir of freshly forged coal dust.
How much dust are we talking about?
We're talking about roughly 230,000 times the mass of the entire Earth, created in one single blinding event. And supernovae do something else that AGB stars cannot. Their explosions are so intense that they force atoms together to forge the heaviest elements on the periodic table.
The iron, the nickel, the cobalt.
The very iron that is, right this second, flowing through the hemoglobin in your blood as you rest, binding to oxygen and keeping you alive. Every single atom of that iron was forged in the blinding heart of an exploding star and violently gifted to the dark.
It is a profoundly comforting thought to know your origins are that spectacular.
So, we have the dust exhaled by the gentle, patient red giants, and we have the massive halls of dust violently scattered by the supernovae.
It is out there.
But once it is released into the void, it has to travel. Let us slow down and follow just one single microscopic grain of olivine, a tiny jagged crystal of stardust, much smaller than a bacterium.
It is embarking on a 100-million-year drift through the interstellar medium, the long, silent, freezing drift. It is a journey defined by profound, almost absolute solitude. The interstellar medium, the vast spaces between the star systems, is almost unimaginably empty. We casually call it a vacuum, but to truly grasp the scale, consider the room you are resting in right now.
The air you are breathing, gently filling your lungs, contains roughly 27 million trillion atoms in every single cubic centimeter. It is a dense, chaotic soup of matter.
But out there, in the deep dark of the interstellar medium, there is, on average, just one single solitary atom per cubic centimeter. The dust grain is drifting through an emptiness so vast and quiet, it challenges the human mind to comprehend it.
And without the warmth of a nearby star, the temperature plummets to realms that are hard to fathom. As this tiny grain of olivine drifts deeper into the great molecular clouds, it plunges into the deep freeze.
Down to near absolute zero.
Roughly minus 263 degrees Celsius, or just about 10 degrees above absolute zero. At that temperature, heat simply ceases to be a meaningful concept.
But as it drifts through this freezing dark, the universe does something incredibly tender. It wraps the grain in a blanket.
It does? Even in that near-perfect vacuum, there are stray atoms and simple molecules slowly floating around. A molecule of water here, a molecule of carbon dioxide there, traces of methane and ammonia.
And because the dust grain is so incredibly, impossibly cold, when one of these wandering molecules happens to bump into our drifting grain of olivine, it does not bounce off.
It sticks. It freezes to the surface instantly. Over the course of millions of years wandering through the dark, the universe quietly wraps every single tiny grain of hard rock in a microscopic layered mantle of ice. It builds a soft, complex, frozen shell around the hard mineral core.
Now, here is where my understanding of chemistry hits a wall. At 10 degrees above absolute zero, everything should be completely locked up, frozen solid. Classical physics tells us that chemical reactions require energy, usually in the form of heat, for atoms to break their bonds and form new ones.
That's right.
Molecules at that temperature shouldn't have the kinetic energy to move, let alone react and build complex structures. It seems like time and chemistry should just stand completely still. How can anything interesting possibly happen in the dark at those temperatures?
If we relied solely on the rules of classical physics, your intuition would be absolutely correct. At 10 Kelvin, atoms do not possess anywhere near the required thermal energy to climb over the activation barriers necessary to chemically bond with one another.
They should just sit there on the icy mantle, frozen, inert, and eternally unchanging.
But here is where the mechanics of the universe become absolutely spellbinding. The universe operates on a deeper, stranger set of rules at the microscopic atomic level, the rules of quantum mechanics. And quantum mechanics allows for a phenomenon known as quantum tunneling.
Tunneling. It sounds like something from a science fiction novel. If I imagine an atom as a tiny marble and the energy barrier as a physical wall, you are saying the marble doesn't need to be thrown over the wall.
Conceptually, yes, but we have to abandon the idea of the atom as a solid marble. In quantum mechanics, particles like hydrogen atoms also exhibit the properties of waves. They exist in a state of probability.
Okay, a state of probability.
Imagine a ball resting at the bottom of a steep valley. In classical physics, to get the ball into the neighboring valley, you have to physically push it all the way up the hill and over the peak. That requires a massive input of energy.
Right.
But in the quantum realm, because the particle is a wave of probability, a small portion of that wave actually bleeds through the physical barrier of the hill. If the particle is light enough, and hydrogen is the lightest element in the universe, it doesn't need the thermal energy to climb the hill.
It simply disappears from one side of the solid barrier and spontaneously reappears on the other. It tunnels straight through the solid wall of the energy barrier.
Wait, if it acts like a wave of probability, is the atom literally in two places at once during the tunnel, or does it just cease to exist on one side and pop into reality on the other? It is more the latter. It is a probabilistic jump. The universe calculates that there is a non-zero chance the particle is on the other side of the uncrossable barrier, and so occasionally it simply is. And this quantum tunneling is the secret engine of life in the universe,
allowing for the slow, infinitely patient, cold assembly of highly complex molecules.
Exactly. Solitary hydrogen atoms land on the icy blanket wrapping our dust grain. They tunnel through the energy barriers to bond with carbon monoxide, creating formaldehyde. They tunnel into other carbon atoms to slowly stitch together polycyclic aromatic hydrocarbons, or PAHs.
And PAHs are crucial, right? They are these complex, ring-shaped molecules made of carbon and hydrogen. They form the fundamental structural scaffolding for almost all organic chemistry.
Precisely. Through the magic of quantum tunneling, the cold dark is weaving the precursors of sugars, of alcohols, of amino acids. Our tiny frozen dust grain is not a dead, inert piece of rock. It is a highly active, meticulous frozen laboratory.
It is patiently synthesizing the complex, life-giving molecules of the universe, hundreds of millions of years before any warm planet or ocean even exists to receive them.
That completely shifts the perspective. The dark isn't dead, it is incredibly busy. It is preparing.
And while this tiny grain is performing quantum chemistry in its icy blanket, it is also engaged in a physical dance. Because these grains, as we mentioned, aren't perfectly round spheres, they are irregular, elongated, slightly jagged little crystals.
And the galaxy is threaded with vast, invisible magnetic fields, stretching across the light years.
As our jagged grain drifts, the faint ambient starlight of the galaxy strikes its irregular edges.
Yes. When you say starlight strikes it, you must remember that light carries momentum. When photons of light hit the asymmetrical edges of the dust grain, they exert a tiny microscopic push. This is known as a radiative torque.
So, if I am picturing a windmill on a farm, the starlight is acting like the wind, catching the angled blades of the dust grain and physically spinning it.
That's an excellent analogy.
Yeah.
The photons transfer their momentum, causing the grain to spin like a microscopic top in the vacuum. And as it spins, hundreds of thousands of times a second, it naturally aligns its longest axis perpendicular to the magnetic field lines of the galaxy.
Imagine trillions upon trillions of these microscopic, ice-wrapped dust grains all spinning softly in the dark, all pointing their compass needles in perfect, silent unison with the galaxy's magnetic pull.
It is a silent, synchronized ballet on a cosmic scale.
Just close your eyes and picture trillions of glittering, spinning tops in the dark. And this alignment is not just a beautiful quirk of physics, it is structurally crucial. because those vast magnetic fields help hold the great molecular clouds together.
They provide a structural tension, balancing against the relentless inward pull of gravity.
The dust grains, by mapping and interacting with these fields, are dictating how the cloud will eventually collapse. They are the unwitting microscopic architects of the future.
And the future is exactly what is coming. Because after millions and millions of years of this solitary drift, of spinning in the magnetic dark, of building complex sugars and PAHs in its ice mantle, the environment of the giant molecular cloud begins to change.
Perhaps a shockwave from a distant supernova ripples through the gas, or the cloud simply crosses a dense spiral arm of the galaxy.
The delicate balance tips. Gravity finally overcomes the outward pressure and the magnetic tension. The cloud begins to slowly, inevitably softly, fall in on itself.
The dust is about to build a home. We're entering the stage of building worlds.
The collapse of a giant molecular cloud is not a sudden, violent event. It is a deeply slow, majestic inward sweep that takes millions of years. But as the vast quantities of gas and dust fall inward, the material collects into denser and denser pockets.
At the very center of one of these collapsing pockets, the pressure and heat build to unimaginable levels until, in a flash of nuclear fusion, a protostar ignites. A new sun is born.
And around that brilliant new star, the leftover material, all the gas, and all those tiny ice-wrapped, chemically rich grains of dust flattens out into a wide, rotating, majestic disk, a protoplanetary disk.
It is a swirling halo of raw, unshaped material. And within this deep, gaseous disk, the dust grains are drifting. They are not moving at tremendous speeds relative to each other.
No, they're moving through the thick gas at the speed of a slow crawl, perhaps a centimeter per second. They're just gently, sleepily drifting, and eventually they bump into each other. When they bump, they stick.
But at this microscopic scale, the gravitational pull between two tiny grains of dust is effectively zero. It is far too weak to pull them together. So what force is actually making them stick?
The force holding them together is a principle of quantum mechanics and electromagnetism known as the van der Waals force. It is a gentle, fluctuating electromagnetic attraction that occurs only when two surfaces get incredibly intimately close to one another.
Like how close?
So close that the electrons in one atom momentarily shift, creating a tiny positive charge on one side and a negative on the other, which induces a mirror response in the neighboring atom, pulling them together.
It is the exact same microscopic force that allows a gecko to walk straight up a perfectly smooth pane of glass.
Really, that's the same force.
Yes, the gecko doesn't have sticky pads. It has millions of tiny microscopic hairs on its feet. When those hairs get flush against the glass, the distance is so unimaginably small that the van der Waals force engages. The molecules of the hair and the molecules of the glass just gently pull at each other.
The dust grains in the protoplanetary disk are acting exactly like the gecko's foot. They brush against each other in the dark, the electromagnetic attraction engages, and they hold on.
And because they are jagged and irregular, they don't pack together into dense spheres. They form these deeply fluffy, highly porous structures, like microscopic, loosely packed snowflakes made of stardust and ice.
And this structural fluffiness is the perfect design for rapid growth. A porous snowflake has vastly more surface area than a solid pebble. It acts like a cosmic net, perfectly designed to catch and trap even more passing grains.
So the fluffy snowflake grows, it aggregates, from a micron to a millimeter to a centimeter. The dust slowly, patiently assembles into pebbles drifting in the disk.
But then as they grow larger, the universe presents a profound, seemingly insurmountable physical challenge. It's a problem in astrophysics known as the meter-sized barrier.
The meter-sized barrier, it sounds like a solid brick wall in space, something that should stop the formation of planets dead in its tracks.
In a mathematical sense, it is a brick wall. As the particles aggregate and grow to the size of a large boulder roughly a meter across, they face a lethal aerodynamic problem. The gas in the protoplanetary disk is orbiting the young star slightly slower than a solid rock naturally wants to orbit.
Why is the gas slower?
This is because the gas has internal outward pressure holding it up, fighting the star's gravity, so it doesn't need to spin at full orbital velocity to avoid falling in. But the solid boulder has no internal pressure support. It is ruled entirely by gravity. It tries to orbit the star at full, mathematically pure speed.
This means the boulder is constantly, relentlessly plowing into a headwind of slower moving gas.
Yes.
If I try to visualize the mechanics of this, I always think of a cyclist fighting the wind. If you are riding a bicycle entirely alone into a strong, stiff headwind, it is exhausting. The wind saps your forward momentum. You have to push so incredibly hard just to maintain your speed, let alone move forward.
For the cosmic boulder, this constant dragging headwind of gas drains its orbital momentum. And in orbital mechanics, if you lose your forward momentum, you lose your altitude. You start to fall.
The boulder begins to spiral inward, doomed to plunge into the fiery, destructive heart of the young star. The physical models show that a meter-sized boulder should spiral to its absolute death in just 1,000 years.
1,000 years is nothing. It's a blink of an eye in cosmic terms. So, theoretically, all the boulders, all the fundamental building blocks of planets should have just burned up in the sun.
And yet here we are, resting peacefully on a rocky planet that is 12 and 1,000 kilometers wide. So the dust absolutely must have found a way to survive the wind.
The answer to this puzzle, how the dust crossed the meter-sized barrier, is one of the most elegant, beautiful mechanisms in astrophysics. It is called the streaming instability.
How exactly does the streaming instability work? Let's go back to the cyclist analogy because that helps ground the physics.
If a cyclist is riding alone, the headwind is mathematically brutal. The drag coefficient is high. But in professional cycling, you rarely see a rider brave the wind alone. They form a group, a peloton.
They huddle together incredibly tightly.
Right. The riders at the very front of the pack take the brunt of the wind, braking it, and the riders behind them draft in the low-pressure slipstream. The whole group moves much more efficiently, conserving massive amounts of energy compared to a single rider. The cosmic dust boulders drifting in the protoplanetary disk do exactly the same thing.
A cosmic peloton of stardust.
Precisely. As the thousands of solitary boulders drift inward, fighting the headwind, natural variations in the gas flow cause some boulders to catch up to others. They form loose clusters, and these clusters act exactly like the cycling peloton.
The leading boulders shield the ones behind from the gas headwind.
Because they're shielding each other, the group as a whole does not lose as much orbital momentum. They slow their inward drift. And because this cluster is now drifting slower than the solitary boulders behind it, it creates a traffic jam.
More and more solitary boulders from behind catch up and join the group. The peloton grows, it becomes thicker, denser, and aerodynamically stronger.
So they are gathering together, hundreds of thousands of boulders riding in the slipstream of the group. But what is the end game here? They can't just keep riding together in a loose cloud forever, can they? At some point, they have to become a planet.
They do, and the transition is stunningly abrupt. Once the peloton of boulders becomes dense enough, once the sheer combined mass of all those rocks huddled together finally outweighs the mass of the gas immediately surrounding them, something instantaneous happens.
The entire loose cluster collapses under the weight of its own collective gravity.
In an astronomical heartbeat, the peloton of loose rocks crunches together into a single, massive, solid body, tens or even hundreds of kilometers across. It becomes a planetesimal.
By grouping together, they survive the headwind long enough to instantly transform into a world massive enough to ignore the wind entirely. It is a beautiful, almost social act of cosmic survival. They literally fall together to save themselves from falling into the sun.
They fall together. I want you to hold on to that image as you relax. The rocks gathered in the dark, drafted off one another and fell into a collective embrace to survive.
It is a rescue mission written into the laws of physics.
And once you have these massive, solid planetesimals, the gentle electrostatic forces are done. Gravity takes the wheel. These massive bodies pull each other in, they collide, they shatter, they merge, and over millions of years, their immense gravity sweeps up the remaining dust to become full-fledged spherical planets.
But what kind of planet they ultimately become, whether they are a rocky world like ours or a gas giant, depends entirely on where they were born in that swirling disk. It depends on a magical, invisible boundary called the snow line.
The snow line is the critical temperature boundary in the protoplanetary disk. Close to the young, burning star in the inner orbits, it is simply too hot for ice to exist in a solid vacuum.
The water, the methane, the ammonia, all those icy blankets that wrap the dust grains vaporize back into gas. So the only solid materials left to clump together and form the peloton are the dry, heavy, rocky silicates and the dense metallic irons.
This is exactly why the inner solar system where we live is populated by small, dense, dry, rocky worlds. Mercury, Venus, Earth, Mars. We are the heavy dregs that could survive the heat.
But if you drift further out into the disk, moving away from the blazing heat of the young star, the temperature drops. Eventually, you cross the snow line.
It is the exact orbital threshold where the ambient temperature drops low enough for all that water vapor to instantly freeze back into solid ice crystals.
Yes. And because the universe is overwhelmingly full of oxygen and hydrogen, the ingredients for water suddenly crossing that line, there is vastly more solid material available to build with.
Ice acts like a profound cosmic mortar.
The planetary cores forming beyond the snow line have so much building material that they grow much larger and much faster than the rocky planets. They grow so massive, so incredibly quickly, that their gravitational pull becomes immense.
They become heavy enough to start pulling in the raw hydrogen and helium gas directly from the surrounding disk.
They wrap themselves in thick, crushing, endlessly swirling atmospheres and become the gas giants: Jupiter, Saturn, Uranus, Neptune.
The simple temperature gradient of that ancient dusty disk, the exact quiet point where water turns to solid ice in the dark, dictated the entire architecture of the solar system we call home.
It is deeply humbling to think that the layout of our entire solar system, the reason Earth is a rocky haven and Jupiter is a massive gas shield, was decided by a simple drop in temperature a few billion years ago.
But here's where the story takes a turn from the grand architecture of the planets straight back into the microscopic. Because not all the dust in that disk melted together to form the Earth.
Not all of it was swallowed by the crushing gravity of Jupiter or burned in the fires of the sun.
Some incredibly ancient solitary grains survived the chaotic, violent birth of the solar system completely intact. They avoided the melting, they avoided the collisions. They just waited patiently in the dark, locked inside primitive rocks waiting to be found.
We are talking about pre-solar grains. True, unaltered stardust. And the absolute best way to understand them is to look at a very unassuming, rather crumbly rock that fell from the sky on the morning of September 28, 1969.
It fell near the small, quiet town of Murchison in Victoria, Australia. It is known to science as the Murchison meteorite.
To the naked eye, if you were to hold it in your hand, it looks like a lump of dark, pitted charcoal. It even smells faintly of sulfur and tar.
But when researchers took this crumbly rock into the laboratory, dissolved away the bulk of the silicates with harsh acids, and looked at the residue under an electron microscope, they found an impossible, miraculous cargo hidden inside.
When I look at a meteorite, I expect to find iron or generic space rock. I certainly don't expect to find diamonds that predate the sun, because that is exactly what they found under the microscope, wasn't it?
It was. Hidden within the matrix of the Murchison meteorite were tiny, absolutely pristine grains of silicon carbide. There were microscopic nanodiamonds forged in the shock waves of supernovae.
There were beautiful bluish crystals of a mineral called hibonite.
And when scientists carefully isolated and analyzed these microscopic specks, they discovered something that challenged our understanding of time. They discovered that these specific grains were over 7 billion years old.
Our sun, the star that gives us light, is only 4.5 billion years old. These microscopic grains predate our entire solar system by more than 2 billion years.
They are older than the Earth you are resting on. They are older than the light of our star. They are messengers from a universe that existed long before we did.
Okay, I have to pause here on behalf of the listener, because this is a massive claim. How can we possibly know the exact age of a microscopic speck of rock? How can we definitively prove it is older than the sun?
If I look at a speck of dust, it just looks like dust. It doesn't have a date stamped on it. What is the physical mechanism that reveals its age?
It comes down to reading the precise nuclear fingerprints locked deep within the atoms of the crystal. Specifically, we look at the isotopes. If we connect this microscopic measurement to a broader, more relatable picture, think of the formation of our solar system like making a massive fruit smoothie in a blender.
A smoothie in a blender. Okay.
You take all the raw ingredients, the strawberries, the bananas, the kale, the apple juice, and you put them in the pitcher. The ingredients represent all the distinct gas, dust, and heavy elements from thousands of different dead stars.
You hit the button, the blades spin, and it all violently whips together into a uniform pinkish-green liquid. Once it is blended, every single sip of that smoothie tastes exactly the same.
It is a perfect uniform average of all the ingredients. Our protoplanetary disk was that blender. All the material was churned, heated, and homogenized.
So everything that formed from that blended material, everything on Earth, every rock on Mars, every asteroid in the main belt, shares a distinct, mathematically uniform isotopic flavor. We know exactly what the solar system ratio of carbon-12 to carbon-13 looks like.
So no matter where you sample the solar system smoothie, whether you take a scoop from the Earth's crust or a scoop from the moon, it mathematically looks and tastes like the solar system. The isotopic ratios are completely uniform.
Exactly. But the pre-solar grains hidden inside the Murchison meteorite were somehow spared. They were physically encased in the rocky matrix of the meteorite before the great solar blender was turned on.
They were never melted down and mixed with the rest of the ingredients.
So when scientists use a mass spectrometer to measure the isotopes, the specific weights of the carbon or silicon atoms in these individual microscopic grains, they don't taste like the uniform smoothie. They taste purely, intensely like a single strawberry, or purely like a single banana.
They carry the highly distinct, unblended, absolutely unique isotopic flavor of the specific long dead star that forged them in its atmosphere 7 billion years ago.
That is genuinely mind-bending. They are completely pristine time capsules, holding the atmosphere of a ghost star.
They are. And it goes even deeper. By analyzing the trace heavy elements trapped inside the silicon carbide grains, elements like barium or strontium, we can literally read the specific nuclear reactions that were occurring inside those dead stars.
We can see the undeniable mathematical evidence of the SPES process, the slow neutron capture process.
This is an incredibly delicate, prolonged nuclear reaction where atomic nuclei slowly absorb free neutrons, one at a time, deep inside the burning shell of an aging red giant. This process builds heavier and heavier elements over millions of years.
When we look at the isotopes in a pre-solar grain, we are literally reading the internal thermodynamic diary of a star that died 7 billion years ago, written on a speck of dust smaller than a human red blood cell.
Yeah, it's just astonishing. But the Murchison meteorite didn't just carry ancient diamonds and the diaries of dead stars. It carried something much more intimately connected to us.
It carried the chemical blueprints for biology. When researchers cracked open that crumbly, foul-smelling rock and carefully analyzed the organic compounds hidden inside the dust matrix, They found amino acids.
The fundamental building blocks of proteins, the structural building blocks of life itself.
And they did not just find a stray molecule here or there. The Murchison meteorite contained a staggering diversity of organics. It held over 90 completely distinct types of amino acids.
To put the magnitude of that discovery in perspective, consider the biosphere of Earth. All of life on our planet, every towering redwood tree, every deep-sea whale, every soaring bird, every microscopic bacteria, and every single human being uses a vocabulary of just 20 specific amino acids to build all the necessary proteins for life.
The universe, functioning in the freezing, irradiated, pitch-black void of the interstellar medium, naturally synthesized those 20 plus 70 more intricate variations that biological life on Earth doesn't even use.
The cosmic dust was generously, patiently preparing a vast buffet of the ingredients for life, hundreds of millions of years before any living thing existed to consume them.
That is a profoundly comforting thought. It shifts the entire perspective of the universe from a cold, empty, hostile void to a meticulous working environment. The universe was just quietly prepping the kitchen, slicing the vegetables, getting the complex ingredients ready billions of years in advance of the meal.
But we aren't just looking at microscopic rocks in laboratories on Earth anymore. Science has moved beyond waiting for the sky to fall to us.
We are looking back out into the deep dark with the most sensitive, powerful eye humanity has ever opened, the James Webb Space Telescope. And the secrets it is whispering to us from the deep past are changing everything we thought we knew about the universe.
The James Webb Space Telescope is a marvel of human engineering, specifically because it operates primarily in the infrared spectrum of light. It does not look for the visible light that our eyes see. It looks for heat,
which makes it the absolute perfect, unparalleled instrument to see cosmic dust. Dust absorbs the hot, blinding blue light of stars and re-emits it as a soft, warm, infrared glow.
And almost immediately after Webb unfolded its golden hexagonal mirrors and turned its gaze toward the deepest cosmos, it started sending back profound surprises. It began to forcefully challenge our mathematical models of how the early universe grew up.
We used to think that the universe needed immense amounts of time to forge enough heavy elements to create dust. Which brings us to a major puzzle. Webb just uncovered the iron dust paradox. Webb pointed its mirrors at a neighboring dwarf galaxy called Sextans A.
Now, Sextans A is what astronomers consider a very primitive, highly metal-poor galaxy. Our standard models, the math we have relied on for decades, dictated that a small, primitive galaxy like this simply shouldn't have forged enough heavy elements to make a significant amount of dust.
It should be a clean, clear, dust-free environment. And yet, Webb looked at an aging, pulsing star in Sextans A, and what exactly did it find hiding in the glare?
It found dust, but it did not find the typical fluffy silicate dust we usually see around dying stars. It found pure, featureless metallic iron dust.
Solid iron grains forming in a metal-poor environment where we previously calculated it was thermodynamically and chemically impossible for them to form in such abundance.
Iron dust is uniquely tricky. It is what we call spectrally quiet. It absorbs visible light and emits infrared heat, but it does so without leaving a sharp, easily identifiable chemical fingerprint in the spectrum, unlike silicates or carbon.
Which means for decades, iron dust was essentially invisible to our older, weaker optical telescopes.
Webb's unparalleled infrared sensitivity showed us that the early, supposedly clean and primitive universe might have actually been deeply, heavily shrouded in solid iron dust that we simply couldn't see. The cosmos was quietly hiding its earliest, heaviest construction work in plain sight.
And if the dust was there much earlier and in much greater quantities than we thought, it explains another massive mystery Webb just recently uncovered. I'm talking about the little red dots.
These strange glowing anomalies showing up in Webb's deepest field images, looking all the way back to the dawn of time. Specifically, there is one anomaly they named Virgil.
Virgil is a truly fascinating object. In the optical spectrum, it is completely invisible. But in Webb's infrared view, it appears as a compact, extremely bright, violently red source of light.
When astronomers broke down the spectrum of Virgil, they realized they were not looking at a normal galaxy. Virgil is an oversized, tremendously active, supermassive black hole.
But it is hiding deep within an incredibly thick, suffocating shroud of red cosmic dust. What makes Virgil so shocking and so rule-breaking is its sheer mass relative to its environment.
Right, because our fundamental assumption was always that a galaxy and the supermassive black hole at its center grew up together, like a tree in its root system. They keep pace with one another.
But you're saying Virgil breaks that rule entirely. How does a black hole outgrow its own host galaxy?
That is the exact question keeping astrophysicists awake at night. In the local modern universe, the mass of a central black hole is almost always directly proportional to the mass of the galaxies surrounding it. They co-evolve.
But Virgil is far too large for the tiny nascent galaxy that hosts it.
It suggests a completely different mechanism for growth in the early universe. Instead of slowly feeding on dying stars over billions of years, Virgil may have been born from the direct, catastrophic collapse of an absolutely massive primordial cloud of gas and thick dust.
The dust is the key mechanism here. It acts as a thermal blanket and a brake. It cools the infalling gas, allowing it to condense and flow directly into the black hole at terrifying speeds, feeding it voraciously without the radiation pressure blowing the food away.
The dust hides the monster, feeds the monster, and glows red with the frictional heat of the meal, completely upending our assumptions about how the first galaxies formed.
It is brilliant how the dust is both the curtain hiding the action and the very reason the action can happen in the first place. But Webb isn't just looking billions of years into the ancient past to watch black holes feed.
It is also looking at relatively nearby solar systems to watch new worlds being born right now. I want to transition to a young star system known as CT Cha, specifically a companion object called CT Cha b.
CT Cha b is a fascinating target. It is a very young, highly massive object, likely a giant planet or brown dwarf, orbiting its host star about 625 light-years away from us.
When Webb directed its infrared gaze at this young, glowing planet, it captured something that theoretical physicists had predicted for a long time, but that human eyes had never directly photographed before: a circumplanetary disk.
So not a massive disk around a star, but a secondary, smaller disk orbiting the planet itself.
Exactly. Imagine a swirling miniature halo of glowing gas and rich dust orbiting directly around the young giant planet. It is quite literally a moon-forming ring.
We are actively watching the dust grains collide, stick together, and build new, solid moons right now, in real time.
And what makes this observation so spectacular is the chemistry. Webb's spectrographs revealed that the chemistry inside that tiny planetary disk is rich with complex carbon-bearing molecules, completely distinct and different from the chemistry of the larger main disk orbiting the star.
The universe is incredibly meticulous. It is constantly sorting, refining, and building complex organic structures with infinite patient variety on the scale of stars and on the scale of individual planets.
When I think of all this, the massive reservoirs of iron dust in Sextans A, the supermassive black holes feeding behind red veils, the complex carbon rings building moons around CT Cha, it paints a picture of a universe that is furiously, beautifully active.
It makes me think about what astronomers poetically refer to as cosmic noon.
Cosmic noon is perhaps one of the most evocative terms in astrophysics. It refers to a specific epoch in the history of the universe, roughly 8 to 11 billion years ago.
If the entire 13.8 billion year lifespan of the universe is a single day, this era was its energetic, blazing midday.
The overall rate of star formation across the entire cosmos was at its absolute staggering peak. Galaxies were furiously, relentlessly churning out new stars, at rates hundreds or even thousands of times higher than our own Milky Way galaxy does today.
And because so many massive, short-lived stars were violently living and exploding in supernovae, the production of cosmic dust was at an all-time historical high.
So the entire universe during cosmic noon was essentially shrouded in a thick, glowing, heavy fog of newly forged stardust.
It was a deeply dusty era. When we use Webb and powerful ground-based radio observatories like ALMA in the Chilean desert to look far back in time to cosmic noon, we see massive, sprawling galaxies that are completely, totally invisible to normal optical light.
The dust is so thick that visible starlight simply cannot escape. But in the infrared wavelengths, those same invisible galaxies blaze with the intense, blinding heat of violent creation.
The dust proves that the universe is not just a vast, empty, sterile void. It is a deeply complex, meticulously active, fiercely creative system.
Even in its most violent, explosive eras of rapid star birth, the dust was there. It was quietly absorbing the dangerous ultraviolet radiation, cooling the ambient gas, shielding the complex molecules, and patiently laying the solid, rocky groundwork for the habitable planets that would inevitably follow billions of years later.
So we have traveled an unimaginable distance tonight. From the violent fires of the Big Bang, through the blazing heat of cosmic noon, deep into the heart of the Milky Way, and into the microscopic diaries locked inside the Murchison meteorite.
But now, as we draw closer to the end of our gentle journey, I want to bring the vastness of the cosmos all the way down. I want to bring it down to the scale of the quiet room you are resting in right now.
Down to the roof over your head and the ground beneath your home. Because this massive billion-year story of cosmic dust is not just a history lesson happening out there billions of light years away. It is an active, ongoing process happening right here, right now, tonight.
It is a continuous, never-ending delivery. Every single day, while we go about our busy human lives, while we work, while we commute, and while we sleep in the dark, the Earth is sweeping up the cosmos.
Our planet, as it hurtles through its orbit around the sun, is constantly plowing through the interstellar medium. Between 5 and 270 tons of cosmic dust fall onto our planet every single 24 hours.
It is a silent, invisible, absolutely relentless rain of stardust. The Earth is not a finished product. It is still growing, adding to its mass, grain by microscopic grain, just as it has for 4.5 billion years.
Where exactly is all that daily dust coming from? We aren't close to any dying red giants right now.
The vast majority of the dust falling on us today comes from comets. Specifically, a group known as Jupiter family comets. These are ancient, dirty snowballs of ice and rock that were perturbed from the outer solar system and pulled into tighter, shorter orbits by the massive gravity of Jupiter.
As these comets loop through the inner solar system, drawing closer to the warmth of the sun, the solar radiation gently sublimates their icy surfaces, turning the solid ice directly into vapor.
And as the ice vanishes into the vacuum, it releases its grip on the ancient embedded dust grains. The comet leaves behind a fine, winding, invisible trail of primitive dust and ancient pebbles scattered across its orbital path.
When the Earth's orbit inevitably intersects one of these cometary trails, we sweep up the particles at tens of thousands of miles per hour. You occasionally see the larger pieces as meteor showers, the brilliant, fleeting streaks of shooting stars burning up high in the mesosphere.
But the vast, overwhelming majority of this cometary material is microscopic. It doesn't burn up. It simply decelerates safely high in the stratosphere, catches the upper atmospheric currents, and drifts like incredibly slow, invisible snow down to the surface.
It is falling on the surface of the wide oceans, slowly sinking into the dark. It is falling on the canopies of the ancient forests. It is falling on the pavement of the streets in your city, and it is settling on the windowsill of your bedroom tonight.
And if you go outside on a perfectly dark, perfectly clear night, far away from the glow of city lights, before the moon rises, You can actually see the collective glow of this dust with your own eyes.
You can. It is a phenomenon called the zodiacal light. It appears as a faint, ethereal, glowing pyramid or column of pale light rising up from the horizon, visible just after sunset in the spring or just before dawn in the autumn.
What you are seeing is not light from our atmosphere. You are seeing the collective reflected glow of trillions upon trillions of tiny dust grains filling the entire inner solar system, catching the sunlight in the dark and scattering it gently back to your eyes.
It is the visible ghost of a million ancient comets, softly illuminating the dark plane of our solar system.
And scientists are not just content to look at the glow. They are actively hunting for these fallen microscopic grains here on Earth, aren't they? And to find them, they have to go to the most isolated, pristine places on the planet.
Yes, they go to the deep, frozen heart of Antarctica. The continental ice sheet there is incredibly pure, largely untouched by terrestrial dirt or human pollution. As the pristine snow falls over the high plateau year after year, century after century, it gently traps the micrometeorites that drift down from the stratosphere.
By drilling deep, long ice cores down into the glacier, scientists can extract solid, frozen layers of ice that are up to 1.5 million years old.
When they take those cores back to a clean room and carefully melt the ice, they find the tiny, dark, magnetic specks of cosmic dust at the bottom of the vial. By analyzing these layers, they are reading a 1.5 million-year-old diary of the Earth's cosmic environment, layer by patient, frozen layer.
These tiny time capsules fell into the snow, and they've been waiting in the freezing dark while early human ancestors evolved, while we invented spoken language, while we invented agriculture, while we invented the scientific method, and finally waited for us to come and carefully dig them out of the ice.
I want you to just lie there, perfectly still, and let this profound thought wash over you. The story we have traced together tonight, the ancient, bloated red giants exhaling their dying, cooling breath into the vacuum, the unimaginably violent flash of the supernovae forging heavy iron in a fraction of a second, the solitary, jagged grain of olivine drifting through the freezing dark for 100 million years.
The gentle physics wrapping that grain in a blanket of water and carbon dioxide ice.
The microscopic quantum tunneling allowing hydrogen atoms to slip through solid barriers to build sugars and complex PAHs.
The vast cosmic peloton of dust boulders drafting off each other, collapsing in an instant to build a solid planet.
None of this majestic history is separate from you. You are not just a distant spectator to this cosmic story, you are the story.
The carbon that forms the intricate double helix of your DNA, the oxygen you are softly breathing in and breathing out right now, the calcium that gives dense strength to your bones.
The iron that is catching the oxygen and carrying it through your bloodstream with every single quiet beat of your heart. All of it followed this exact, unhurried journey.
You are an unimaginably complex, completely unrepeatable, highly organized arrangement of ancient stardust. You are a collection of atoms that have survived the violent death of massive stars, the deep absolute freeze of the interstellar vacuum, the chaotic, fiery birth of a solar system, and billions of years of slow, patient, earthly evolution.
And right now, those ancient, enduring atoms are just lying in the dark of your room, breathing softly, resting after a long journey. You are perfectly at home in the cosmos because you are fundamentally the cosmos.
That realization, that deep biological connection to the stars, brings us to one of the most profound, lingering questions we can ask in astronomy, the Fermi paradox.
If the universe is so incredibly demonstrably generous with its raw materials, if the organic chemistry of life, the amino acids and the complex sugars, are actively forming on the icy mantles of dust grains in every cold molecular cloud, in every single galaxy, constantly, across 13 billion years of deep time, why is the universe so quiet?
Why haven't we heard a signal from anyone else? If the fundamental ingredients for biology are literally everywhere drifting in the dark, Where's everybody?
It is a profound question, and for some, it is a question that can make the sheer vastness of the universe feel terribly lonely. But if we connect this silence back to the broader, deeply physical picture of the cosmic dust, it doesn't have to feel lonely at all.
Because what the dust definitively tells us is that the universe is a continuously, endlessly, meticulously recycling system. It does not hoard its valuable materials, it shares them. It scatters them violently into the dark so that entirely new, complex things can be built.
The dust grain itself doesn't know any of this, of course. The microscopic crystal of silicon carbide doesn't know it is 7 billion years old. The universe did not set out from the Big Bang with a conscious architectural plan to build a human being.
But through the relentless laws of physics, the inevitability of quantum chemistry, and the infinite forgiving patience of deep time, it did. You are the universe, folded temporarily into a biological form, looking back at itself. You are the ancient dust, finally capable of feeling the beauty and the weight of its own long origin.
As you drift closer and closer to sleep, I want to leave you with one final, deeply peaceful thought. Something to let your wandering mind float upon as the conscious demands of the waking world fade entirely away. Think about the sheer physical endurance of the individual atoms that make up your body right now.
They have traveled through the void for billions of years, surviving unimaginable extremes of heat and cold, just to become you today.
But your existence, as profound as it is just a single chapter in their incredibly long story. Billions of years from now, long, long after the Earth has finished its story and been swallowed by our own swelling sun, the atoms currently forming your hands, your eyes, and your heartbeat will not be destroyed.
They will simply be released. They will drift back up into the quiet dark. They will return to the vast interstellar medium. They will eventually find themselves deep within a new, cold molecular cloud.
They will be wrapped in fresh, pristine blankets of ice. They will fall together in a new, streaming instability, spinning in the magnetic dark to build a new peloton.
And eventually, after another eternity of patience, they will become the deep bedrock, the rolling oceans, or the breathable atmosphere of an entirely new world, orbiting a young, bright star that hasn't even been born yet.
Your atoms have an absolute eternity of journeys ahead of them. They have all the time in the universe. And so do you tonight. Rest well, breathe slowly, sleep deeply. You are safe, you are ancient, and you are exactly where you are meant to be. Good night.